Welcome to the deep dive. We take complex research, slice right through it, and pull out the key stuff you need to know. Today, we're diving into the physics of fluids and gases. You know, the everyday mechanics behind water, air, how planes fly, all that.
Yeah, it's a pretty big scope today. We've sifted through a lot of physics material, really fundamental principles about liquids and gases. We're going from like tiny molecular forces that make water act weirdly, all the way up to atmospheric pressure and, well, lift.
Right, and we should mention, we leaned on some great instructional summaries. A quick nod to physics teachers everywhere, like Haki Valley Tarun mentioned in the sources. Folks who make the stuff make sense.
Absolutely. So we're digging into things like pressure, surface tension, buoyancy, Bernoulli's principle, stuff that honestly shapes our whole world.
Okay, Ben, let's unpack it. Starting small.
Yeah.
Really small, with that weird skin on water.
Right, surface tension. So it starts with the molecules. Inside the liquid, okay, they're pulled pretty much equally every way. But the ones right at the surface, they don't have neighbors above them.
Ah, okay. So they only get pulled sideways and, crucially, downwards, towards the rest of the liquid.
Exactly. That creates this net downward pull. It tenses up the surface, almost like a stretched film kind of elastic.
Okay, like a trampoline skin. But why does it do that? What's the point?
Well, the point is energy. Physics loves the lowest energy state, right? That surface layer, it's actually high energy, so the liquid tries to minimize that surface area. Less surface, less energy needed.
Got it. And that's why drops are spheres, because a sphere is the shape with the least surface area for its volume.
Here we go. Insight number one. Drops are round because liquids are, well, kind of lazy energy-wise.
Huh, okay. And the skin, this tension, how strong is it, really?
Surprisingly strong. Strong enough that things a bit denser than water can actually sit on top. Think about a water strider bug, or even if you carefully place a razor blade flat on the water.
Yeah, you can see the surface bend down a bit, like a little dent, but it doesn't break through.
Right, that's the surface tension holding it up. It's a real physical force from those molecules pulling together.
That's wild. Okay, does it change? Like if you heat the water, does that affect the tension?
Oh, absolutely. And this is a really neat point from the sources, maybe a bit counterintuitive. Hot soup. It actually has lower surface tension than cold soup.
Lower.
Huh.
So heating it up makes the molecules jiggle more, weakens that pull between them?
Precisely. More kinetic energy disrupts that cohesion.
Okay, so if hot liquid has less tension, does that mean it spreads out easier, wets things better?
You got it. Lower tension means it's less inclined to stick to itself, more willing to spread. And that idea, that balance between sticking to itself, cohesion, and sticking to other things, that leads right into capillarity.
Capillarity. Right, that's when liquid seems to climb up inside narrow tubes.
Yeah.
Or sometimes sink down, even tiny tubes, like 0.5 millimeter.
Yeah, exactly. And what's happening there is basically a fight, a tug of war. It's between cohesion, the molecules pulling on each other, and adhesion, the molecules being attracted to the walls of the tube.
So if the liquid likes the tube walls more than it likes itself, adhesion wins and it climbs up.
Right. It pulls itself up the walls. But if the liquid's molecules are more attracted to each other, cohesion wins, and the surface level actually dips down in the middle.
And this isn't just some lab curiosity, is it? This happens all over.
Oh, constantly. It's how plants pull water way up from their roots against gravity. It's fundamental. It's why your paper towel soaks up a spill, the liquid climbs into the tiny fibers. Same reason your towel gets wet or moisture wicks through clothes.
Wow. So these tiny molecular forces, adhesion and cohesion, they're driving really big visible effects.
Totally. It's molecular attraction scaling up to macro level stuff.
Okay, that connects the small scale nicely. Now let's zoom out, way out. From tiny forces to the huge one all around us, the atmosphere, its weight.
Yeah, we're shifting gears now from forces and drops to, well, forces measured in tons.
Yeah.
Air has weight. Simple as that. It might not feel like much, but at sea level, around 20 Celsius, air density is about 1.2 kilograms per cubic meter.
1.2 kilos per cubic meter. And there's a lot of cubic meters above us, so we're living at the bottom of an ocean of air, essentially.
That's a perfect analogy. And it's heavy. That weight creates pressure.
And the classic experiment showing this pressure is Torricelli's barometer, right, with the mercury.
Right. Back in the 17th century, he showed that the weight of the atmosphere, the pressure, could hold up a column of mercury 76 centimeters high, 760 millimeters.
Okay, mercury's dense. What about water? How much water can that same air pressure hold up?
That's the number that's really relevant day to day, especially if you think about diving or pumps. Atmospheric pressure can support a column of water about 10.3 meters high.
10.3 meters. Okay, that's the key connection for people, because if you dive down 10.3 meters...
You've got the entire atmosphere pressing down on the surface, plus the weight of that 10.3 meters of water above you.
So you're experiencing double the pressure. One atmosphere from the air, one from the water.
Exactly. 2 atmospheres total.
Ah.
And it just keeps increasing. Go down another 10.3 meters, you're at 3 atmospheres. It's linear.
That's a really clear benchmark. Okay, so we've got this pressure idea. What about gases when they're contained, like in a tank or a tire? That brings us to Boyle's law, right?
Yep, Boyle's law. This describes how pressure and volume relate for a gas if you keep the temperature the same, like in a sealed container. And the relationship is fundamentally inverse.
Inverse proportion, meaning if you squeeze the gas into a smaller volume...
its pressure goes up. Cut the volume in half, the pressure doubles. P times V stays constant, essentially. P euro equals P euros.
Right. And we see this everywhere. Pumping up a bike tire, right? You're forcing more air into the same volume, basically, increasing pressure. Or aerosol cans.
Exactly. And critically for divers, again, think about the air in their lungs. As they come up from depths, the outside water pressure decreases.
So the air inside their lungs must expand, according to Boyle's law.
Right. And managing that expansion, usually by exhaling steadily, is absolutely vital for safety. You can't just hold your breath on ascent.
Wow. So that simple inverse relationship, PV constant, has life or death implications. Okay. Let's shift from static pressure and contained gases to things in motion. Buoyancy first. The lifting effect of air.
Yes, so buoyancy isn't just for boats in water. Air provides buoyancy too. It's Archimedes' principle again. An object in a fluid, and air is a fluid, experiences an upward buoyant force equal to the weight of the fluid it displaces.
So if an object can displace a weight of air that's greater than its own weight, it floats, it lifts.
Precisely, which leads us right to the classic example.
Hot air balloons.
Hot air balloons. We know normal air has that density, about 1.2 kilograms per cubic meter. When you heat the air inside the balloon envelope,
It expands, becomes less dense than the cooler air outside.
exactly. So the balloon, even though it's huge, is now filled with this big volume of less dense air. It displaces a large volume of the heavier, colder air around it.
Yeah.
The weight of that displaced cold air is significant.
And if that weight is more than the total weight of the balloon fabric, the basket, the burner, the people...
Then the upward buoyant force wins, and up you go, lift off.
Simple displacement, but with density differences playing the key role. Okay, this is great. But now, the big one. The really dynamic principle. Bernoulli's. This explains so much about high-speed stuff in fluids.
Ah, yes, Bernoulli's. And if we really connect this to the big picture, this principle is behind some truly amazing visible phenomena. The core idea is actually kind of backwards to how you might first think about it.
Okay.
Bernoulli's principle states that for a fluid, like air or water, as its speed increases,
Yeah.
its internal pressure decreases.
Wait, faster flow means lower pressure or not higher?
Lower pressure. Speed is the enemy of pressure, you could say.
Yeah.
Where the fluid moves fastest, the pressure is lowest.
That is wild. Okay, so how does that explain something like flight?
Okay, think about an airplane wing, an airfoil, especially shape, right? Curved on top, flatter on the bottom.
Right.
That shape forces the air flowing over the top curved surface to travel a longer distance in the same amount of time as the air flowing underneath.
Longer distance, same time. So the air on top has to move faster than the air on the bottom.
Exactly. Faster air on top means lower pressure on top, according to Bernoulli,
And the slower air underneath has relatively higher pressure.
creating a net pressure difference. Higher pressure below pushing up, lower pressure above sort of pulling up. That imbalance is lift.
Wow, just from shaping the wing to make air move at different speeds, that's incredible.
It is. And this isn't just for airplanes. You see Bernoulli effects in some surprising places.
Real quick.
Okay, get this. Strong wind blowing horizontally across a flat roof. That fast-moving air above the roof has low pressure.
Okay.
But the still air inside the attic, or the house, is at normal, higher atmospheric pressure. That pressure difference can actually push the roof upwards, make it bulge out, or even lift off in a storm.
Seriously, the wind isn't pushing the roof down, it's creating low pressure that lets the inside pressure push it up. That's genuinely scary.
It can be. Same principle, different fluid.
Mm-hmm.
Think about two ships sailing parallel, really close to each other. The water funneled into the narrow gap between them has to speed up to get through.
Ah, faster water in the gap means lower pressure in the gap.
Lower pressure right there between the holes. The normal higher pressure on the outer sides of the ships then pushes them towards each other into the low pressure zone.
So they can actually get sucked together. just because of the water speed.
It's a known hazard in navigation, yeah.
Yeah.
That pressure drop can be strong enough to cause collisions if they're too close and moving too fast.
Man, these fluid dynamics are powerful. It even applies to small things, right? Like, didn't the source mention carburetors?
It did, yeah. Old school carburetors use a Venturian-narrowed passage to speed up the incoming air,
Faster air, lower pressure.
which then sucks the fuel into the airstream to mix with it. Same principle again, using speed to create a pressure drop.
It's amazing how that one core idea, faster flow, lower pressure, shows up everywhere, from flight to ships to engines.
It really ties a lot together, doesn't it? So if you step back, we've gone from, the tiny molecular pole creating surface tension,
Yeah.
enough to float a razor blade,
Yeah.
through the sheer weight of the atmosphere, holding up meters of water,
Right, that 10.3 meters.
and landed on these dynamic principles where fluid speed dictates pressure, lifting planes, and even threatening ships or roofs.
It shows how these concepts, which seem maybe complex at first, are all built on pretty fundamental observations and relationships, like that inverse link between speed and pressure.
Exactly. It's all connected. The physics on the small scale influences the large scale, and the principles governing stationary fluids also help explain fluids in motion.
A really cool journey through these invisible forces.
Definitely. And maybe one final thought for you to chew on, connecting back to that pressure idea.
Okay.
We established that atmospheric pressure, just the weight of the air, can support a column of water about 10.3 meters high.
Right. That's its limit, essentially.
So think about a vacuum pump trying to lift water. A perfect vacuum pump works by removing all the air pressure above the water inside the pipe. Right. It creates suction.
Yeah, so the outside atmospheric pressure is what actually pushes the water up the pipe into the vacuum.
Exactly. So if the atmosphere's pushing power is only strong enough to lift water 10.3 meters, what does that tell you about the absolute maximum height any suction pump, no matter how perfect, could ever lift water using just atmospheric pressure?
So the pump isn't pulling, the atmosphere is pushing,
Mm-hmm.
and it can only push so hard. Interesting. Something to think about.